Welcome. In this lecture, we're going to talk about respiration during exercise and what kind of goes into that with your pulmonary system. And so it'll connect to our circulatory system. They're very interconnected, and so you should be able to make those connections as we go through as well. A lot of this will be kind of review of basic anatomy, structure, and function, and then just kind of relating it back to exercise towards the end. So remember, purpose of our respiratory system is to provide pulmonary respiration, so ventilation through the exchange of O2 and CO2 in the lungs that goes into the blood and then eventually to the rest of the tissues for cellular respiration. And we've talked about the importance of those two things, of why we have O2 and then getting rid of CO2. And so when we look at this during exercise, it's really about this gas exchange between the environment and the body to keep these energy systems rolling, especially our oxidative systems, and to get some byproducts out from glycolysis, so that buildup of lactic acid and being able to buffer that acid-base balance so that it doesn't become too out of hand and cause detriments to our enzymes and other functions in the body. So with our respiratory system, we're really trying to replace the O2 we utilized in the blood. We're trying to remove CO2, and then we're trying to regulate that acid-base balance. And we do that through ventilation, the mechanical process of moving that air in and out of the lungs. And so once the air gets to kind of an endpoint in our lungs, we then use diffusion, which allows molecules to move from a high concentration to a low concentration in order to get those to exchange. So diffusion is simply moving things from a high concentration to low, and that's what happens in the lungs. You have a high amount of oxygen, so it moves into the blood, and you have a low amount of CO2, which moves out of the blood, and then you again ventilate, so you move that air out of the lungs, goes back into the environment, and then you change those levels of O2 and CO2 back in the lung when you breathe back in. And so this is kind of an overview of what that looks like. So air containing high O2, air containing high CO2 coming out, O2 coming in, goes into our alveoli, goes into the blood, goes to the tissues where that exchange happens, comes back to the lungs, and then out. And so our respiratory system has a structure to it. So most of us know about things like our lungs and our trachea, but you also have to consider the nose and the nasal cavity and pharynx. You have your bronchioles and your bronchus. And so what that does is that really divides our respiratory system into two systems. The conducting zone, which is simply designed to move air in and out of the environment into our body, or really into our lungs. And then our respiratory zone, which is where the actual exchange of gases happen in the blood. And so that respiratory zone is really small, goes into our alveoli and our alveolar ducts. Really the last little bit, the microscopic portions, would be considered our respiratory zone. And so you can kind of see how they're positioned in the body. There is a protective sac around them. There's this pleural cavity, which allows for, it's kind of dead space. There's nothing really there. And it allows for when your diaphragm moves, for there to be a pressure gradient to draw air into the lungs or force air out of the lungs if that's compressed. Again, this kind of overviews those respiratory zones and pulmonary zones. Again, those respiratory zones are where typically we think of that air exchange actually happening, especially at the lower levels, these alveolar sacs and ducts, because they're small, they're tiny, and they have very thin walls, which will make a difference for diffusion. And the upper area, the conducting zones, are where we just simply are using those tracts to move air in and out. Not really any exchange happens into the blood or anywhere else there. It's just a tube to help get the air down out of the environment down into our alveolar sacs. And so you can kind of see that here. What's really cool is the surface area of your lungs. So the idea of your lungs and all of these kind of tubes getting smaller and smaller and leading to other places is to increase surface area, because the larger the surface area, the more oxygen we can diffuse into the blood or CO2 out. So what's really crazy is your lungs. You can think about how big they are. If you were to actually take and lay it out flat, kind of cut open and get every flat surface just to lay side by side, your lungs actually have the surface area about the size of a tennis court. which is really cool. That's a large surface area for air to be touching inside of you to be able to have diffusion happen. So really all the surface area in the lungs is about the size of a tennis court if you could stretch it all out and see it, which is pretty crazy. So in the alveolar wall, this is where most of our exchange happens, and that's because we have capillaries running on just the other side of the wall. So it's a very thin, one cell layer thick cell wall here at the alveoli, and there's blood vessels running through, and it allows for CO2 to go in and CO2 to go out into the alveoli and O2 to come in. So we want there to be a lot of blood flow to these areas, and we want it to be very thin for diffusion to happen quickly. So ventilation is the movement of air. It occurs because of bulk flow, so it's really just a pressure differential. When there's a lot of pressure in the lungs, we want to force air out. When there's not as much pressure, we tend to draw air in. And so inspiration occurs because of the lung volume increasing, expiration because that is decreasing, and there are changes in our chest that cause this to happen. And so you can see here your diaphragm is the main thing causing this change in capacity. So whether it's large or whether it's small, drawing air in or drawing air out. When your diaphragm contracts, it's a domed shaped muscle. It flattens out and increases the space the lungs can take up and draws air in. When your diaphragm relaxes, you exhale because the space gets smaller and it forces that air out. And you can see as the chest cavity what happens here, and your rib cage actually comes up as well. And so you can see the muscles involved with that: diaphragm, intercostals, external intercostals as well. And so this all brings us to what we call airway resistance. I realized I scrolled a little too far. Airway resistance. And so this is just talking about airflow happens because we have two different pressures, and then there's resistance to that. And so think about blowing up a balloon. There's a lot of resistance to that, so you have to provide more pressure to blow that up. But larger areas you can just kind of fill up with air because there isn't a lot of resistance. If you've ever opened up a bottle that you've squeezed all the air out of and you open up the cap and it just kind of sucks it in very easily. Resistance was low, pressure differential was high enough, and we had this airflow. This becomes an issue when you start talking about certain diseases like COPD, chronic obstructive pulmonary disease, or asthma. All of these increase resistance to the airways and make it harder for people to breathe because the pressure differential is a little bit different, and so airflow doesn't happen as easily. Let's see, and so it's really important for you to know some of these terms like tidal volume, dead space, inspired, expired, because they come up a lot in the pulmonary system. And so pulmonary ventilation, again, that movement of air in and out, is simply determined by how much volume of air you move with every single breath times how many times you breathe per minute. And we get that number that goes up with exercise. Not only do you breathe more in and out every single time you breathe during exercise, you also breathe more frequently to get CO2 out and to get oxygen in. But part of that is we have this alveolar ventilation, so how much is moving in and out of the alveoli versus how much is moving in and out of the conducting zone. And so this creates what we call dead space ventilation, where a lot of the air that we actually breathe in stays in our bronchioles and our trachea, and in our mouth we have air right now, and we're not utilizing that. We can't actually have gas exchange occur there, and so that's called dead space because it doesn't reach the alveoli, the respiratory exchange area, and so really nothing's occurring with that gas. So we have to make sure we're getting fresh air into the alveolar space. So we have alveolar ventilation, which is the actual air that we can exchange gases, O2 and CO2. And so just because you're breathing in a lot, if it's not getting all the way down, if you're taking really rapid breaths and not exchanging that air in the alveoli space, the alveolar space, you're not actually getting you're not having diffusion occur because CO2 is building up too high and O2 concentrations are too low. So these give some basic definitions and values to some of the things that are referred to here. So respiratory volumes, so tidal volumes, the amount of air inhaled and exhaled in one breath just kind of while you're sitting there. So as you're watching this video, just kind of tidal volume is the natural amount of air you're taking in and out on a regular resting basis. But you have inspiratory reserve volume, which is the maximum amount of air that you can breathe in at a given time. So if you took in the biggest breath you could, that would be inspired reserve volume. So how much more air can you take in than your actual tidal volume? Expiratory reserve volume would be the maximal amount of air you can breathe out, in addition to your tidal volume that we have here. So how much more can you breathe out than what you currently are? And then residual volume is how much air remains in your lungs after you blow out or you exhale as much as you possibly can. There will always be air left. We don't create a vacuum in your lungs even when you breathe out. There's always going to be air left. And so then we get into some things that can kind of help us see how much air, again, we continue to move. So you've got total lung capacity, which is how much air your lungs can actually hold. Functional residual capacity is their amount of air remaining in the lungs following a normal expiration. So functional residual capacity, so you just breathe, you exhale normally, how much air is left. So this is the extreme residual volume. Functional residual capacity is how much naturally you have left in your lungs. Inspiratory capacity, the maximum amount of air that you can inhale from a normal expiration. So you exhale normally, and then how much more air could you take in on top of that? And then your vital capacity is how much air you can forcefully exhale after a maximal inspiration. So breathe in as deep as you can, exhale as much as you can. What is that? So that's the maximum amount of air you can move in a single breath. And this is done through spirometry, which is simply where there's a machine that measures the air you take in and take out and can measure those volumes and whether it's coming in or coming out, and you can start seeing that. And this is an example of that. They make much smaller versions now too that work. And what it does is it plots a graph. So as it goes up, you're breathing in. As you're going down, you're breathing out. And so normal breath tidal volume is here. They take a biggest breath they can. It goes all the way up. This would be there. And respiratory reserve volume is the difference between here and here. Inspiratory capacity is this whole curve all the way there. That's how much they can breathe in with a normal expiration. They go back to breathing normal. Expiratory reserve, how much is there left, how much they can expire beyond the normal. Functional residual capacity is how much they can exhale. Functional residual capacity is how much air is left in the lungs with a normal exhalation. Residual volume, maximal exhalation, what they have left. Vital capacity, what you can actually utilize of your lungs, and then total lung capacity as well. So the important thing to look at here is they have, this can help determine certain issues people have, and we can start to see why they become an issue. So a normal person, this blue line, they can exhale a whole lot of air very quickly from their lungs. So you can exhale 60-70% of the air in your lungs within the first second of forcefully exhaling air out of your lungs. If you took a big breath in, and you can see that it's a steep curve, and then you kind of level off. Well, someone with COPD, chronic obstructive pulmonary disease, there's a lot of airway resistance, and they can't force that air out as easily. And so it takes them a long time to fully exhale, and they don't actually exhale as much air as a normal person. And so this leads to some issues. And so another thing to talk about when it comes, not only is it important to look at airflow and that process, but you also need to consider, well, what's happening with the gases inside of that air. And so we have Dalton's Law of Partial Pressures, which basically says that you can take the percentage of each gas in a particular gas mixture. So if you take normal room air, we can figure out what percentage is O2, CO2, nitrogen. We can figure out what the barometric pressure is in the room, and basically those percentages correspond. So if you have 20.93% of O2 in the air and your barometric pressure is 760, that means you have a partial pressure of oxygen of 159. So that means that oxygen is trying to push into something with 159 millimeters of mercury of pressure. And those all add up together. And the reason this is important is we can start to calculate the fact that, remember, diffusion is high concentration to low concentration. So if we know the partial pressure of how much oxygen is there and CO2 and nitrogen, we can know what the exchange is if it comes up to a gas that is different. So when you breathe in room air, this is room air numbers, your O2 percentage is smaller, your CO2 percentage is higher, your nitrogen is about the same. And so we can see the pressure differentials, and we can actually calculate how much air will be exchanged. The greater the difference in the partial pressures, the more oxygen or CO2 atoms would be exchanged. The smaller the number, the less exchange occurs. And so along with this, you have what's called Fick's Law of Diffusion, which is talking about the rate of gas that will be diffused across a particular area. So think from the lungs into the blood, or from the blood into the lungs. And so that has to do with the partial pressures. That has to do with the tissue area. So that goes back to why it's great that our lungs take up so much surface area, about the size of a tennis court. The tissue thickness makes a difference. So we get down to that alveolar level where the cell wall is only one cell layer thick, because that allows for diffusion to happen more quickly and more easily. And so all of these make a difference. And so what you see is you can actually start to calculate how much air is moving in which direction. And you can follow this from exchange of O2 to the arteries from the veins and the lungs. And then at the tissue level, it kind of gets reversed. And you can follow these partial pressures and see how things are moving over time. So to get that exchange. So then you have blood flow to the lungs. So the pulmonary circuit gets about the same amount as a systemic circuit that we really talked about in the circulatory chapter. It is a low pressure area, so you're not getting shouldn't be getting high pressure in the lungs like you do at the arteries and the main arteries in your systemic circuit. Most of the blood flow actually goes to the base of the lung, so the bottom of the lungs during rest. So gravity just kind of pulls that blood lower. During exercise, more of the entire lung blood flow is increased to the entire lung, and you see a better dispersion of that blood across all of the lung area, not just at the base. But this does make a difference, and so you can kind of see this blood flow starts at the top, goes to the bottom, and so the blood tends to, at rest, pull at the bottom, but during exercise, we actually perfuse more of the lung, and so we get to take advantage of more of that surface area and have greater oxygen and CO2 exchange. And this kind of is illustrated here based on kind of the bottom of the lungs, and it's kind of where they're at, located to ribs to the top, and how much blood flow is there. A lot is happening at the base, but again, that will change with exercise. And so what you really want is you want your blood flow to ventilation to match. So we want there to be a certain ratio of blood flow to ventilation, because what that means is that we're getting the maximum amount of exchange, and if that ratio is too low or too high, we're not getting the exchange we should. We're either not getting enough oxygen and CO2 exchange, or we have way too much and we're actually leaving some on the table. And so at rest, the base has a very over-perfused area, and so we're actually leaving oxygen that we could utilize somewhere, like we could absorb, but it's being left in the lungs. In the apex of the lungs, it's being under-perfused, meaning it's not getting enough oxygen and CO2 exchange, and that causes issues there. And so you can kind of see that during upright exercise, so light to moderate exercise, we actually improve this ratio. It becomes more even across the board, and then during heavy exercise, especially really, really heavy exercise for an intense amount of time, we may have issues with this ratio again, and that causes fatigue and causes where we can't go on. And again, a good little picture there. So all of that to be said, we do have to talk about the transportation of oxygen and even CO2 when it comes to the blood. And so, yeah, we can get that oxygen into the lungs, we can diffuse it over into the blood, but what happens there? How do we get it to the tissue? And so realize that 99% of the oxygen that we breathe in is transported by hemoglobin. So you've heard of this. This is kind of in your red blood cells. So it's called oxyhemoglobin if O2 is bound to that hemoglobin, or deoxyhemoglobin if O2 is not bound. So at the tissue side, after it passes through tissue, it's going to be deoxyhemoglobin. We hope it's unloaded that oxygen. at the lung side, after it goes through, we hope its oxyhemoglobin has picked up O2. That's not happening. That could be an issue on its own. And so we can actually calculate how much O2 can be transported through your blood. And that's because we know that for each gram of hemoglobin that you contain, that you have in your body, that'll carry about 1.34 milliliters of oxygen. So that's a measurement. And these are all considered at sea level. So realize all of the numbers we've talked about so far are at sea level. The pressure of oxygen changes as you go up. So if you've ever heard of someone going up a mountain and become harder to breathe, it's not because there's less oxygen or less air. There's actually the same percentage of oxygen in the air. It's just the pressure is lower, and so we don't see that exchange happening as readily. It's not as dense with that pressure. And so oxygen is usually 100% saturated. You can do an O2 saturation. It's really close to 100% saturation of that hemoglobin with oxygen. And so if we know how much can be held per gram, and we know that usually it's fully saturated, we also have determined that males typically contain about 150 grams per liter of blood, and females contain about 130 grams of hemoglobin per liter of blood. And so if you know about how much blood they have, and you know these numbers here, you can quickly estimate about how much oxygen they can move per liter of blood, and then per their whole body as well, if you can do that estimate. And so you can see the amount of O2 that we're delivering. It's a decently large amount, considering a liter of blood can hold 200 milliliters of O2, but that's not a lot, and so we have to continue that circulation through exercise, and intense exercise. We have to move a lot more blood to keep that oxygen up. You may ask yourself, why do males have higher rates than females? Well, it tends to go back to some hormones and just sex differences, but we know that males tend to carry more iron and process iron a little bit better. Males are less likely to become anemic, which is missing iron, where females are more likely, and so it really has to do with this concentration of iron and hemoglobin in males and females that leads to males tending to be able to carry more oxygen and thus being a little bit better at endurance style exercise. Everything else held constant. That doesn't mean a female can't be better than a male. It just means if everything else is equal, males will carry more oxygen per liter of blood, and statistically makes them a little bit better at that endurance exercise. And so basically what happens, deoxyhemoglobin plus O2 gives us oxyhemoglobin. The direction of this kind of equation, you see how the arrow goes back and forth, really depends on where the blood's at. So at the lungs, we see this deoxyhemoglobin to oxyhemoglobin. At the tissues, because there's low levels of oxygen, we see the oxygen offload again through diffusion and become deoxyhemoglobin, which is kind of explained there. And so that brings us to what we call the oxygen hemoglobin dissociation curve. So if we look at a gram of, or really any kind of level, but a gram of hemoglobin, at a certain pressure of oxygen in millimeters of mercury, we know what that percentage, how much of that hemoglobin is going to have oxygen attached to it. So at 100 millimeters of mercury, you have 100% saturation. And then as that goes down, we see that oxygen offloads. So at the first little bit of drop, we only lose a little bit of oxygen. And then all of a sudden, we have this steep drop as we go. So there's a bigger and bigger offload of oxygen at a lower and lower concentration at every single step of concentration of your partial pressure. And so this is what occurs. So typically what you see is the amount of O2 offloaded at tissues is about 20%, 25% or so of that oxygen is offloaded at tissues from the lungs, from the blood after it goes to the lungs. But if we start falling below that, so we start putting more demand on the body and those pressures get even lower, the body starts giving a higher and higher percentage of oxygen with every small change because it wants to make sure that you're getting enough oxygen to those areas to keep them alive, to keep energy processes flowing so it doesn't die. And so this steep curve makes sure that if somewhere is having an issue, we're going to unload more and more until it becomes either catches back up or maybe it can't catch back up when we get to 0. And so there are things that affect this, such as pH and temperature. And so what you can see is that this curve can shift depending on pH. So it can become where in a pH environment, so if it drops lower, that means our blood's becoming more acidic. The O2 offloads quicker. Usually this is because we sense that lactic acid is building up and our pH is dropping due to that, and so we want to get more oxygen in to change those energy systems to our oxidative phosphorylation and Krebs cycle. If it's more basic, we hold on to more of that because we're not worried about glycolysis building up some lactic acid. We may actually want it to build that up. Temperature, same kind of thing. Cool temperatures, we hold on to it a little easier. High temperatures, we get rid of it a little easier because we want to make sure that our body has enough energy to keep ourselves cool. And so then we have myoglobin, which is our O2 shuttle from basically where it comes out of the bloodstream, where O2 comes out of the bloodstream, and get it into the mitochondria for use. This is done by myoglobin. Myoglobin actually has a higher affinity for O2, so if you put the two together, myoglobin is going to take oxygen before hemoglobin, and this is a good thing because it can help store oxygen in our muscles, like keep it there in case there's a blood flow issue, kind of like a reserve in case things pick up quickly. But it also helps to buffer that O2 with initial startup of exercise, and has a quick way to get O2 if those pressures drop too much. And so you can see that dissociation curve. Myoglobin wants to hold on to oxygen until the very, very end where pressures get really, really low. Again, keeping that reserve just in case something goes wrong with some of the blood flow. So we talked a lot about the oxygen, so now we need to flip over and talk about CO2 transport. So O2 transport was through hemoglobin. CO2 transport actually happens in 3 ways. So some of it will get dissolved in the plasma in the blood, and that happens. A little bit of it will actually bind to hemoglobin, so some of the CO2 will bind to hemoglobin and then be taken back up to the lungs, but a majority of it is transferred through what we call the bicarbonate system. And this is where you take CO2 and H2O through carbonic anhydrase, and you make bicarbonate, which quickly dissociates to bicarbonate acid and the hydrogen there. And so you can see this exchange that occurs here. All 3 of them are listed, but again, a majority of it is happening through this bicarbonate system, which kind of buffers our pH. And so what you can see is with pulmonary ventilation, you can see that in the muscle, we go from CO2 and H2O to bicarbonate, and then in the lungs, we reverse that. It goes either way very quickly, very easily. Think about how long that blood is near the alveoli where that exchange can happen. This happens very quickly and allows that CO2 to come out of the blood into the lungs for exhalation. And so the reason that this happens is kind of good because then it also kind of helps us to know when we need to ventilate more, when we increase ventilation. So if you increase the amount of CO2 that your body's producing, and most of it's carried in this way, what happens is you start to increase the amount of hydrogens that are in your blood, which drops the pH, making you more acidic, and your body can sense this hydrogen concentration and the pH decreasing, and this causes you to breathe more to get the CO2 out. Decreased ventilation can occur because we are not having this buildup of hydrogens, and we're not seeing that decrease in pH. And so part of the reason we actually breathe more a lot of times is to get CO2 out and to buffer those hydrogens. To breathe CO2, we're getting rid of that hydrogen atom, so we're increasing our pH level, we're making it less acidic. And so this is a lot of the reasons we actually breathe more than to get oxygen in. We have a lot of oxygen, we need that as well. It's kind of part of the process, but a lot of times that breathing actually is occurring more because of getting CO2 out than it is getting O2 in. So if you were to hold your breath right now and hold it until you feel like you can't anymore, actually if we were to measure your blood gases, it would be more to the fact that you have this buildup of bicarbonate and these hydrogen ions and you can't get CO2 out, more than it is not getting oxygen in. And so if you hold your breath until you feel like you can't, you start breathing out, not breathing in, but you start breathing out first, it'll actually take some of that sensation away for the beginning because you buffer that feeling. And that's kind of seen here. They do happen together. You have that drop in O2, you have the increase in PCO2, and that causes your ventilation to go up to get more O2 in and more CO2 out. And this is with exercise, and so you're going to see that drive in needing O2 before you see that production of CO2 occur. Again, just kind of think about your energy systems and how they relate. Additionally, you can see this with exercise. During exercise in a hot, humid environment versus cold, PCO2 stays the same, but our ventilation, PCO2 stays the same throughout that exercise, but you see the ventilation going up, and that is because you're ventilating more because you need to get rid of more CO2. You want to keep this at the same level, and your energy systems are working harder to keep you cool in the heat. And so we do want to talk about the fact that there are changes in ventilation. So there are not a lot of changes in our actual anatomy of the lungs like we see in muscles and things like that. We don't have these big changes necessarily in those systems and the way they work and how they operate, but we do see that the body becomes more accustomed and better able to utilize oxygen and move things through the blood and at the lungs between people that are trained and untrained. And so what happens is an untrained individual, their PO2 goes down, and then it just gets to a point where their body can't really function. It doesn't know how to continue to withdraw oxygen from that, and they kind of are unable to keep exercising. Where in an elite runner, they're going to follow that same kind of curve. It's a little bit not as steep, but then at the very end, their body is able to pull a lot more oxygen off of that blood at the end to be able to go for just a little bit longer or a little bit higher intensity. Same thing with pH. pH's body is able to keep it constant, pretty close, and then there's this linear drop-off where an elite runner, it just kind of tends to hold a little stronger and more of a gradual decline until the very end where there's a steep drop-off. Same thing with ventilation, this pretty steep increase through the whole thing, where with an elite runner, it's linear but not as steep, and then just at the very top of their ability, you see this drastic increase. So their body's able to kind of at this 75% level be able to utilize better, and then once they get over that, their body just goes right back, and you can see the extremes are hit very close to the same. So we do have changes to our breathing during exercise. So you can see the tidal volume during rest and how that tidal volume, not only we take quicker breaths as the intensity goes up, but we take deeper and deeper breaths and we inhale and exhale more. The good thing is that a lot of this control for our ventilation we don't actually have to think about, which is nice. A lot of our inspiration and expiration is done through the brain centers, especially the initial kind of part of this that gets everything up and going. But then we also have input from respiratory control centers, so chemoreceptors in our blood measuring the PCO2 or hydrogen concentrations in different areas that are sensitive to these, or measuring the amount of the pressures of O2 and potassium in the blood. All of these help to regulate it more at a fine-tuned control. So brain centers help with those big movements, and then we fine-tune our breathing and respiration rates with these receptors. And so we have this neural input that's coming in. We can actually affect this for a short time, but then our automatic brain centers will take over. We don't have to think about increasing that breathing or really breathing at all anytime during the day. And so you can see how there's this giant feedback loop between the heart and also the lungs. This talks about those brain centers and how they work. The good thing to note is that our lungs are way overbuilt. Our lungs are built way more than what we need. We're able to move more air, oxygen, CO2. And so when it comes to exercise, our limits are not usually from our lung capacity and our ability to move air in and out or even exchange that air. It more comes down to our muscles and our energy system to be able to utilize that. It's going to hold us back. And so you can see arterial PaCO2 and ventilation, how it's really a strong driver. The higher those PaCO2 levels, the higher those levels of bicarbonate, the more that's going to drive our breathing. But we do know that O2 will do that as well if it gets too low. So hypoxic threshold, you're not getting enough oxygen. We see this big increase in ventilation. Just like we see the high CO2 levels driving that, but it's more linear with PCO2 and O2. It stays pretty constant until we get to the point of not having enough oxygen in parts of our body, and then we increase that breathing rapidly. So ventilatory control during exercise, again, submaximal exercise, primarily driven by higher brain center, central command, fine-tuned by those chemoreceptors and neural feedback. Heavy exercise, it's really this high concentrations of CO2 and these low concentrations of O2 that are continuing to drive that up and up. And so you can see all of these things playing in. Respiratory muscles do play an effect in this as well because they're being utilized more. Let's see. So continuing to talk about exercise with this, 20 to 30% ventilation is low during exercise following endurance training. So basically, as you go to endurance training, you're actually going to need to breathe less. Again, because it's not the lungs that are necessarily holding you back. Your body's learning how to utilize that oxygen more in the body. It's learning how to make those systems operate at a better rate instead of just needing to bring in more oxygen and get rid of CO2. It's learning how to utilize those products. Additionally, we're increasing capillary flow, and so we have increased capillaries in the lungs, and so we do see some more exchange happening as well. So that, think about that ratio we talked about before. So before training, after training, you can kind of see that, and again, less feedback to the muscle stimulating breathing, less production of that hydrogen atoms. Again, we don't really alter that lung structure. We may increase some capillary flow, getting that ratio right, but there's not a lot of that. Normal lung exceeds gas exchange demand even at high trainings. And so we're perfectly capable of handling that even in an untrained individual. Low to moderate intensity, our pulmonary system is never the limiting factor. High intensity exercise, exchange is not the limitation in healthy individuals at sea level. If you change from sea level, go up into the mountains, that can become an issue. Muscle fatigue at high intensity can start to limit. So basically your lung muscles start to get tired. So sometimes you may feel that stitch kind of in your lungs if you've been going for a little while at a high intensity. But again, it's not the ventilatory capacity and the gas exchange, it's more those muscles getting tired and just need to train to go a little bit longer. So in some elite athletes, hypoxia can be a limiting factor. Really high extreme, so basically they start pulling too much out. But this is usually for a short time, and they know not to kind of push themselves to that area. So that concludes our lecture on the pulmonary system. If you have any questions, let me know. Hope you guys are enjoying this course so far.